Start off with Andre.
Okay, hi everyone, welcome. My name is Andre, and I lead the vision team here at Tesla Autopilot, and I'm incredibly excited to be here to kick off this section, giving you a technical deep dive into the Autopilot stack and showing you all the under-the-hood components that go into making the car drive all by itself. So here I'm showing the video of the raw inputs that come into the stack, and then neural network processes that into the vector space. And you are seeing parts of that vector space rendered in the instrument cluster on the car. What I find kind of fascinating about this is that we are effectively building a synthetic animal from the ground up. Roughly 4 years ago, the car was mostly driving in a single lane going forward on the highway. And so it had to keep lane and it had to keep distance away from the car in front of us. And at that time, all of processing was only on individual image level. So a single image has to be analyzed by a neural net and make little pieces of the vector space, process that into little pieces of the vector space. So on the bottom, we have a lot of neurons that are really scrutinizing the detail of the image. And on the top, we have neurons that can see most of the image and a lot of that context, have a lot of that scene context. We then like to process this with feature pyramid networks. In our case, we like to use BiFPNs. And they get to multiple scales to talk to each other effectively and share a lot of information. So for example, if you're a neuron all the way down in the network and you're looking at a small patch and you're not sure if this is a car or not, it definitely helps to know from the top layers that, hey, you are actually in the vanishing point of this highway. And so that helps you disambiguate that this is probably a car. So this is for the detection by itself. Now, very quickly we discovered that we don't just want to detect cars, we want to do a large number of tasks. So, for example, we want to do traffic light recognition and detection, a lane prediction, and so on. So very quickly, we converge in this kind of an architectural layout where there's a common shared backbone and then branches off into a number of heads. So we call these, therefore, HydraNets, and these are the heads of the Hydra. This architectural layout has a number of benefits. So number one, because of the feature sharing, we can amortize the forward pass inference in the car at test time. And so this is very efficient to run. Because if we had to have a backbone for every single task, that would be a lot of backbones in the car. Number two, this decouples all of the tasks, so we can individually work on every one task in isolation. And for example, we can uprev any of the data sets or change some of the architecture of the head and so on, and you are not impacting any of the other tasks. And so we don't have to revalidate all the other tasks, which can be expensive. And number three, because there's this bottleneck here in features, what we do fairly often is that we actually cache these features to disk. And when we are doing these fine-tuning workflows, we only fine-tune from the cached features up and only fine-tune the heads. So most often in terms of our training workflows, we will do an end-to-end training run once in a while where we train everything jointly. Then we cache the features at the multi-scale feature level. And then we fine-tune off of that for a while. And then end-to-end train once again, and so on. So here's the kinds of predictions that we were obtaining, I would say, several years ago now, from one of these HydraNets. So again, we are processing individual images. There we go. We are processing just individual image, and we're making a large number of predictions about these images. So for example, here you can see predictions of the stop signs, the stop lines, the edges, the cars, the traffic lights, the curbs here, whether or not the car is parked, all of the static objects like trash cans, cones, and so on, and everything here is coming out of the net, here in this case, out of the HydraNet. So that was all fine and great, but as we worked towards FSD, we quickly found that this is not enough. So where this first started to break was when we started to work on Smart Summon. Here I am showing some of the predictions of only the curb detection task, and I'm showing it now for every one of the cameras. So we'd like to wind our way around the parking lot to find the person who is summoning the car. Now the problem is that you can't just directly drive on image space predictions. You actually need to cast them out and form some kind of a vector space around you. So we attempted to do this using C++ and developed what we call the Occupancy Tracker at the time. So here we see that the curb detections from the images are being stitched up across camera scenes, camera boundaries, and over time. Now there were two major problems, I would say, with the setup. Number one, we very quickly discovered that tuning the Occupancy Tracker and all of its hyperparameters was extremely complicated. You don't want to do this explicitly by hand in C++. You want this to be inside a neural network and train that end to end. Number two, we very quickly discovered that the image space is not the correct output space. You don't want to make predictions in image space. You really want to make it directly in the vector space. So here's a way of illustrating the issue. So here I'm showing on the first row the predictions of our curbs and our lines in red and blue. And they look great in the image, but once you cast them out into the vector space, things start to look really terrible, and we are not going to be able to drive on this. The other problems with this, by the way, is also for object detection. If you are only making predictions per camera, then sometimes you will encounter cases like this where a single car actually spans 5 of the 8 cameras. And so if you are making individual predictions, then no single camera sees all of the car. And so obviously you're not going to be able to do a very good job of predicting that whole car. And it's going to be incredibly difficult to fuse these measurements. So we have this intuition that what we'd like to do instead is we'd like to take all of the images and simultaneously feed them into a single neural net and directly output in vector space. Now this is very easily said, much more difficult to actually achieve. But roughly, we want to lay out a neural net in this way, where we process every single image with a backbone, and then we want to somehow fuse them, and we want to re-represent the features from image space features to directly some kind of a vector space features, and then go into the decoding of the head. Now, so there are 2 problems with this. Problem number 1, how do you actually create the neural network components that do this transformation? And you have to make it differentiable so that end-to-end training is possible. And number 2, if you want vector space predictions from your neural net, you need vector space data sets. So just labeling in images and so on is not going to get you there. You need vector space labels. We're going to talk a lot more about problem number 2 later in the talk. For now, I want to focus on the neural network architectures, so I'm going to deep dive into problem number 1. So here's the rough problem, right? We're trying to have this bird's eye view prediction instead of image space predictions. So for example, let's focus on a single pixel in the output space in yellow. And this pixel is trying to decide, am I part of a curb or not, as an example. And now, where should the support for this kind of a prediction come from in the image space? Well, we know roughly how the cameras are positioned and their extrinsics and intrinsics, so we can roughly project this point into the camera images. And the evidence for whether or not this is a curb may come from somewhere here in the images. The problem is that this projection is really hard to actually get correct because it is a function of the road surface. The road surface could be sloping up or sloping down, or also there could be other data-dependent issues. For example, there could be an occlusion due to a car. So if there's a car occluding this viewport, this part of the image, then actually you may want to pay attention to a different part of the image. So in order to solve this issue, we use a transformer to represent this space. And this transformer it uses multi-headed self-attention and blocks of it. In this case, actually, we can get away with even a single block doing a lot of this work. And effectively what this does is you initialize a raster of the size of the output space that you would like, and you tile it with positional encodings with sines and coses in the output space. If you do all of the engineering correctly, this again is very easily said, difficult to do. You do all of the engineering correctly. There's one more problem actually before. So one more thing, you have to be careful with some of the details here when you are trying to get this to work. So in particular, all of our cars are slightly cockeyed in a slightly different way. And so if you're doing this transformation from image space to the output space, you really need to know what your camera calibration is. And you need to feed that in somehow into the neural net. But actually, we found that we can do much better by transforming all of the images into a synthetic virtual camera using a special rectification transform. We insert a new layer right above the image, rectification layer. It's a function of camera calibration, and it translates all of the images into a virtual common camera. So once you do this, this improves the performance quite a bit. So on the left, we are seeing what we had before, and on the right, we're now seeing significantly improved predictions coming directly out of the neural net. This is a multi-camera network predicting directly in vector space, and you can see that it's basically night and day. You can actually drive on this. And this took some time and some engineering and incredible work from the AI team to actually get this to work and deploy and make it efficient in the car. This also improved a lot of our object detection. So for example, here in this video, I'm showing single camera predictions in orange and multi-camera predictions in blue. And basically, if you can't predict these cars if you are only seeing a tiny sliver of a car. So your detections are not going to be very good, and their positions are not going to be good. But a multi-camera network does not have an issue. Here's another video from a more nominal sort of situation. And we see that as these cars in this tight space cross camera boundaries, there's a lot of jank that enters into the predictions. And basically, the whole setup just doesn't make sense, especially for very large vehicles like this one. And we can see that the multi-camera networks struggle significantly less with these kinds of predictions. OK, so at this point, we have multi-camera networks, and they're giving predictions directly in vector space. But we are still operating at every single instant in time completely independently. So very quickly, we discovered that there's a large number of predictions we want to make that actually require the video context, and we need to somehow figure out how to feed this into the net. So in particular, is this car parked or not? Is it moving? How fast is it moving? Is it still there, even though it's temporarily occluded? Or for example, if I'm trying to predict the road geometry ahead, it's very helpful to know if the signs or the road markings that I saw 50 meters ago. Now, I'm going to go into both of these blocks one by one. Also, in addition, notice here that we are also feeding in the kinematics. This is basically the velocity and the acceleration that's telling us about how the car is moving. So not only are we going to keep track of what we're seeing from all the cameras, but also how the car has traveled. So here's a cartoon diagram illustrating some of the challenges here. There's going to be the ego car is coming from the bottom and coming up to this intersection here, and then traffic is going to start crossing in front of us, and it's going to temporarily start occluding some of the cars ahead. And then we're going to be stuck at this intersection for a while and just waiting our turn. This is something that happens all the time and is a cartoon representation of some of the challenges here. So number one, with respect to the feature queue and when we want to push into a queue, obviously we'd like to have some kind of a time-based queue where, for example, we enter the features into the queue, say, every 27 milliseconds. And so if a car gets temporarily occluded, then the neural network now has the power to look and reference the memory in time and learn the association that, hey, even though this thing looks occluded right now, there's a record of it in my previous features, and I can use this to still make a detection. So that's kind of like the more obvious one, but the one that we also discovered is necessary in our case is, for example, suppose you're trying to make predictions about the road surface and the road geometry ahead, and you're trying to predict that I'm in a turning lane and the lane next to us is going straight. Then it's really necessary to know about the line markings and the signs, and sometimes they occur a long time ago. And so if you only have a time-based queue, you may forget the features while you're waiting at your red light. So in addition to a time-based queue, we also have a space-based queue. So we push every time the car travels a certain fixed distance. So some of these details actually can matter quite a bit. And so in this case, we have a time-based queue and a space-based queue to cache our features, and that continues into the video module. Because of the structure of the problem, we're driving on two-dimensional surfaces. We can actually organize the hidden state into a two-dimensional lattice. And all I want you to see basically is that there's cool activity as the recurrent neural network is keeping track of what's happening at any point in time. And you can imagine that we've now given the power to the neural network to actually selectively read and write to this memory. So for example, if there's a car right next to us and is occluding some parts of the road, then now the network has the ability to not write to those locations. But when the car goes away and we have a really good view, then the recurrent neural net can say, okay, we have very clear visibility. We definitely want to write information about what's in that part of space. So here we are making predictions about the road boundaries in red, intersection areas in blue, road centers, and so on. So we're only showing a few of the predictions here just to keep the visualization clean. And yeah, this is done by the Spatial RNN. And this is only showing a single clip, a single traversal, but you can imagine there could be multiple trips through here, and basically a number of cars, a number of clips could be collaborating to build this map, basically and effectively an HD map, except it's not in a space of explicit items, it's in a space of features of a recurrent neural network, which is kind of cool. I haven't seen that before. The video networks also improved our object detection quite a bit. So in this example, I want to show you a case where there are two cars over there, and one car is going to drive by and occlude them briefly. So look at what's happening with the single frame and the video predictions as the cars pass in front of us. Yeah, so that makes a lot of sense. So a quick playthrough through what's happening. When both of them are in view, the predictions are roughly equivalent. And you are seeing multiple orange boxes because they're coming from different cameras. When they are occluded, the single frame networks drop the detection, but the video module remembers it, and we can persist the cars. And then when they are only partially occluded, the single frame network is forced to make its best guess about what it's seeing, and it's forced to make a prediction, and it makes a really terrible prediction. But the video module knows that there's only a partial, it has the information, and knows that this is not a very easily visible part right now, and doesn't actually take that into account. We also saw significant improvements in our ability to estimate depth, and of course, especially velocity. So here I'm showing a clip from our remove the radar push, where we are seeing the radar depth and velocity in green, and we were trying to match or even surpass, of course, the signal just from video networks alone. And what you're seeing here is in orange, we are seeing a single frame performance, And in blue, we are seeing, again, video modules. And so you see that the quality of depth is much higher. And for velocity, the orange signal, of course, you can't get velocity out of a single frame network. So we just differentiate depth to get that. But the video module actually is basically right on top of the radar signal. And so we found that this worked extremely well for us. Here's putting everything together. This is what our architecture roughly looks like today. So we have raw images feeding on the bottom. They go through a rectification layer to correct for camera calibration and put everything into a common virtual camera. We pass them through RegNets, residual networks, to process them into a number of features at different scales. We fuse the multi-scale information with BiFBN. This goes through a transformer module to re-represent it into the vector space in the output space. This feeds into a feature queue in time or space that gets processed by a video module, like the Spatial RNN, and then continues into the branching structure of the HydraNet with trunks and heads for all the different tasks. On the right, you are seeing some of its predictions. This architecture has definitely complexified from just a very simple image-based single network about 3 or 4 years ago and continues to evolve. It's definitely quite impressive now. There's still opportunities for improvements that the team is actively working on. But this basically is how you achieve a very nice vector space. And now I believe Ashok is going to talk about how we can run planning and control on top of it.
Thank you, Andre. Hi, everyone. My name is Ashok. I lead the planning and controls, auto labeling, and simulation teams. So, like Andre mentioned, the vision networks take dense video data and then compress it down into a 3D vector space. Even back in 2019, our planner was pretty capable driver. It was able to stay in the lanes, make lane changes as necessary, and take exits of the highway. But city driving is much more complicated. Rarely there are structured lane lines. Vehicles do much more free-form driving than the car has to respond to all of cuttons and crossing vehicles and pedestrians doing funny things. What is the key problem in planning? Number one, the action space is very non-convex. And number two, it is high-dimensional. There can be multiple possible solutions that can be independently good, but getting a globally consistent solution is pretty tricky. So there can be pockets of local minima that the planning can get stuck into. And secondly, the high dimensionality comes because the car needs to plan for the next 10 to 15 seconds. It needs to produce the position, velocities, and acceleration over this entire window. This is a lot of parameters to produce at runtime. Our solution to this entire problem is to break it down hierarchically. Let's see an example of how the search operates. So here, we're trying to do a lane change. In this case, the car needs to do 2 back-to-back lane changes to make the left turn up ahead. For this, the car searches over different maneuvers. So in the first one it searches is a lane change that's close by, but the car brakes pretty harshly, so it's pretty uncomfortable. The next maneuver it tries does the lane change a bit late, so it speeds up, goes behind the other car, goes in front of the other cars, and finally does the lane change. But now it risks missing the left turn. We do thousands of such searches in a very short time span. Because these are all physics-based models, these futures are very easy to simulate. And in the end, we have a set of candidates, and we finally choose one based on the optimality conditions of safety, comfort, and easily making the turn. So now the car has chosen this path, and you can see that as the car executes this trajectory, it pretty much matches what we had planned. The cyan plot on the right side here, that one is the actual velocity of the car, and the white line underneath it was the plan. So we are able to plan for 10 seconds here and able to match that when we see in hindsight. So this is a well-made plan. When driving alongside other agents, it's important to not just plan for ourselves, but instead we have to plan for everyone jointly and optimize for the overall scene's traffic flow. In order to do this, what we do is we literally run the Autopilot planner on every single relevant object in the scene. Here's an example of why that's necessary. This is an auto corridor. I'll let you watch the video for a second. Yeah, that was Autopilot driving in an auto corridor, going around parked cars, cones, and poles. Here, there's a 3D view of the same thing. The oncoming car arrives now, and Autopilot slows down a little bit, but then realizes that we cannot yield to them because we don't have any space to our side. But the other car can yield to us instead. So instead of just blindly braking here, Autopilot reasons about that car has low enough velocity that they can pull over and should yield to us because we cannot yield to them, and assertively makes progress. A second oncoming car arrives now. This vehicle has higher velocity, and like I said earlier, we literally run the Autopilot planner for the other object. So in this case, we run the planner for them. that object's plan now goes around their side's parked cars, and then after they pass the parked cars, goes back to the right side of the road for them. Since we don't know what's in the mind of the driver, we actually have multiple possible futures for this car. Here, one future is shown in red, the other one is shown in green. The green one is a plan that yields to us. But since this object's velocity and acceleration are pretty high, we don't think that this person is going to yield to us, and they are actually going to go around these parked cars. So Autopilot decides that, OK, I have space here. This person is definitely going to come, so I'm going to pull over. So as Autopilot is pulling over, we notice that that car has chosen to yield to us based on their yaw rate and their acceleration. And Autopilot immediately changes its mind and continues to make progress. This is why we need to plan for everyone, because otherwise we wouldn't know that this person is going to go around the other parked cars and come back to their side. If we didn't do this, Autopilot would be too timid and would not be a practical self-driving car. Finally, we do a continuous optimization to produce the final trajectory that the planner needs to take. Here, the gray thing is the convex corridor, and we initialize a spline in heading and acceleration, parameterized over the arc length of the plan. And you can see that the optimization continuously makes fine-grained changes to reduce all of its costs. Some of the costs, for example, are distance from obstacles, traversal time, and comfort. For comfort, you can see that the lateral acceleration plots on the right have nice trapezoidal shapes. It's going to come up for, yeah, here on the right side, the green plot. Has a nice trapezoidal shape, and if you record a human trajectory, this is pretty much how it would look like. The lateral jerk is also minimized. So in summary, we do a search for both us and everyone else in the scene. We set up a convex corridor and then optimize for a smooth path. Together, these can do some really neat things like shown above. Here, this is a parking lot. The ego car is in blue, and it needs to park in the green parking spot here. So it needs to go around the curbs, the parked cars, and the cones shown in orange here. So it is a simple baseline. It's a A-star, it's a standard algorithm that uses a lattice space search. And the heuristic here is a distance, the Euclidean distance to the goal. So you can see that it directly shoots towards the goal, but very quickly gets trapped in a local minima. And it backtracks from there, and then searches a different path to try to go around this parked car. Eventually, it makes progress and gets to the goal, but it ends up using 400,000 nodes for making this. If you added a navigation route to it, and has the car to follow the navigation route while being close to the goal, this is what happens. The navigation route helps immediately, but still, when it encounters cones or other obstacles, it basically does the same thing as before, backtracks and then searches a whole new path. The navigation heuristic helped, but still this took 22,000 nodes. The vision networks produces a vector space, and we have cars moving around in it. This basically looks like an Atari game, and it's a multiplayer version. So here, again, the same problem. Let's see how MCTS tree search does. So here you notice that the planner is basically able to, in one shot, make progress towards the goal. To notice that this is not even using a navigation heuristic. Just given the scene, the planner is able to go directly towards the goal. All the other offshoots you're seeing are possible options. It's not choosing any of them, just choosing the option that directly takes it towards the goal. The reason is that the neural network is able to absorb the global context of the scene and then produce a value function that effectively guides it towards the global minima as opposed to getting it stuck in any local minima. So this only takes 288 nodes and is several orders of magnitude less than what was done in the A-star with the Euclidean distance heuristic. So this is what a final architecture is going to look like. The vision system is going to crush down the dense video data into a vector space. It's going to be consumed by both an explicit planner and a neural network planner. In addition to this, the network planner can also consume intermediate features of the network. Together, these produce a trajectory distribution, and it can be optimized end-to-end, both with explicit cost functions and human intervention and other imitation data. This then goes into explicit planning function that does whatever is easy for that and produces the final steering and acceleration commands for the car.